Hi, everyone, and welcome to Math 5620 Analysis 2. My name is Dr. Quinn Morris, and I will be your instructor for this course. So to begin, before we jump into material, I just want to take a little bit of time and talk about how this course follows from Math 5610 Analysis 1 and what we'll be doing with our time during this semester. So the first question you might ask is, well, what's new? What are we going to be doing? How are we going to extend what we learned in Math 5610? So if you think back to Math 5610, we focused most of our work on the analysis that was sort of relevant to understanding the theory and the proofs behind the major results from Calculus 1 and 2. So for example, we talked first about sort of some basic topology of R in the hopes of then understanding a little bit about limits. Once we understood some about limits, then we moved to continuity, properties of continuous functions, then to differentiation, functions or theorems about differentiable functions, and then finally on to integration. So we spent much of that 5610 really just looking at real valued functions of a single variable. So functions from R to R. In Math 5620, we're going to sort of split our time between two different things. But the first thing we're going to look at is really looking at the theory and proofs behind the major theorems from Calculus 3, where we examine functions of several variables. So that might be functions which take multiple inputs and spit out a single real value. That might be functions which take a single real value as an input and spit out a vector value, right? So vector value functions, and it might be a vector valued function of several variables. So it takes n inputs and spits out m outputs. And we'll talk more about all of that as we go. But the first half of the course, we want to sort of spend looking at that. And then the second half of the course, we will look more deeply into integration, in particular, a new type of integration called Lebesgue integration. Now, as far as what you'll be asked to do in this course, it will be very similar to Math 5610. So you'll be asked to watch recorded lecture videos and complete some activities. You'll be asked to complete exercise sets to help you strengthen your knowledge. And you'll also be asked to demonstrate your mastery of the material on both midterm and final exams. So as far as the actual structure of the course goes, it will look very similar to Math 5610. Each week, 3 videos will be released, one on Monday, one on Wednesday, one on Friday. Although it is possible that from time to time, instead of releasing one video on a Monday, I could release 2 short videos. But there'll be videos released each of those days, Monday, Wednesday, and Friday, typically in the afternoon. And then exercise sets will be posted each Thursday, and they will be due 8 days later. So not the Friday that's the next day, but a week from that Friday. That should give you plenty of time to look at the exercise sets, work on them, reach out to me if you have questions, and get a final submission in by that following Friday. Now, as far as a more specific plan for the semester, again, as I mentioned, you can think about breaking this into roughly sort of 2 halves, and really it will split more or less around the spring break period, which is March 9th through 13th. So in the first half of the course, we're going to extend those concepts of differential and integral calculus that we learned in Math 5610 to functions of several variables. So we're going to look at first the structure of sort of n-dimensional Euclidean space, or Rn. We'll look at different kinds of functions of several variables. So we'll look at scalar fields. We'll also look at vector fields. Again, we'll talk more about exactly what those are and how we think about them. And then, again, we want to deal with both differential and integral calculus of those types of functions. So we'll look at limits, continuity, and differentiability in higher dimensions. And we'll also look at different types of integrals. So, for example, line integrals, surface integrals, multiple integrals. And of course, we'll want to tie all that together in the end with some of the major theorems that you would have seen in Calc 3. So divergence theorem, Stokes theorem, Green's theorem, etc. So we'll spend roughly the first half of the course looking at that material. In the second half of the course, we will return to sort of this idea of integration. We'll go back to just looking at mostly single variable functions, so functions from R to R. And we'll try to think about how we might extend the notion of the Riemann integral to a wider class of functions. This will actually require us to develop a new kind of integral called the Lebesgue integral. And in order to do that, we'll first need to develop the notion of the Lebesgue measure for subsets of R. Once we have that, we'll then be able to develop this new Lebesgue integral, look at properties of that integral, and finally tie everything up with some convergence theorems related to the Lebesgue integral. So that will be our plan for the semester. Again, that'll split pretty evenly in half. And hopefully throughout the semester, we will not only strengthen some of our knowledge from 5610 as we revisit it and look at it in a new context, but also get to explore some new material and expose you at least a bit to the idea and the notions of measure theory, which you could go on and study more in depth in further graduate studies. We'll stop there for now. In the next video, we will jump right into the course material. But for now, I just want to welcome you and say I'm excited to work with you this semester. And as always, if you have any questions, please feel free to reach out to me via email or phone.